Okay, FOCS-twins. Now, pay attention, because this is going to lead us ultimately to a very important popular algorithm in computer science with very important, impact on practice. Okay. Now, every year when I teach this class, I pick a random student. Let's call that student S1, and I ask, "What's your birthday?" And then I see if someone in the class matches that birthday. And if so, I say we have identified a FOCS twin. Okay, so FOCS twins are students with matching birthday. Okay, those are FOCS twins. And 1 year, okay, I haven't taught this class that many times, but 1 year, when I picked the student, boom! Someone had a matching birthday, and we said, yippee! And we were all thrilled because, this looks like some kind of magical miracle. It's like an extreme coincidence. Right? How likely is it? I pick a random student, and someone in the class of approximately 200 students has a matching birthday. Okay? But on some years, I fail. And if I fail, then I'll go to the second student. I'll pick another second random student and ask, "What's your birthday?" and see if there's a FOCS twin. And if I fail, I'll pick a third and a fourth and a fifth. So I might go to, student 3, student 4, student 5, Maybe I'll go to student 10. If I fail, I might keep failing and go to student 25. I might keep failing and go to student 100. And we're wondering, wow, this could be a very tedious class. It turns out, that I've never had to go beyond student 5, in order to find a FOCS twin. And if I had to go beyond student 10, I would be utterly surprised. Okay? So now let's see why. Let's analyze this peculiar coincidence. Okay? And we will show that it is actually reasonably likely that I will succeed on student 1. It's a super coincidence, but it looks like a super coincidence, but it's reasonably likely that I will succeed. Okay? So let's analyze this phenomenon. So imagine that I define the events. So I'm going to ask students. So I'm going to define the event A1. When I pick the first student, is the event student 1 has no FOCS twin. Okay, and A2, the event that student 2 has no FOCS twin. And let's suppose that there are 200 students, although we could make this argument for n students. So AN, AN is the event that student S200. So S200 has no FOCS twin. Okay. And what's going on here? Okay, so let's analyze these events. So let's, for example, consider what's the probability that the first student has no FOCS twin, that A1 occurs. Okay, what's the probability of A1 occurring? So let's draw a picture of what's going on. So imagine that I list the birthdays, and rather than call the days January 1st, January 2nd, and so on, I'm going to be very boring and just call the birthdays 1, 2, 3 up to B. So the birthdays are 1, 2, 3, 4, and so on, up to birthday B. And B is 366. Okay? And we're interested in the situation where the student S1 has no FOCS twin. Okay, so let us assume, now since we're talking about birthdays, so if I pick a random student of my 200 students, and look at their birthday, the outcome is the birthday. So there are B outcomes, and I'm going to assume that all possible birthdays are equally likely. So it's a uniform probability space. So let's make the assumption that all birthdays are equally likely. Okay. And we'll make another assumption, and we'll see, what that other assumption is and where we need it. But you should be able to guess what that assumption is because we're talking about independence. We will assume that if you pick two students randomly, and if I tell you, okay, Joe's birthday is, January 19th, and now I picked another student. Here's Anna. What's Anna's birthday? You're like, what? How should I know? And the idea here is that, knowing Joe's birthday doesn't tell you anything about Anna's birthday. So the birthdays of students are independent. Birthdays are independent. Okay. Now these are both two approximations. I mean, statisticians have studied when are people born, and some days might be more likely than others. It turns out that we can relax that first condition. We don't need it. The chances of finding FOCS twins are going even higher if all birthdays are not equally likely. As an extreme case, imagine that all people are born on the first day, so only one day is likely. Then I'm guaranteed to find a FOCS twin by the first student. Okay, so all birthdays being equally likely, that just simplifies the analysis. Birthdays are independent is more or less true, except in peculiar situations like, for example, twins. If you have a pair of twins, knowing the birthday of one of them tells you the birthday of the other. So they're not independent. But by and large, birthdays are independent. Okay, so now let's analyze the probability that student 1 has no FOCS-twin. Okay, so the situation is like this. Student 1 is born on some day, let's say January 9th. Okay, but, I can call January 9th day 1. Okay, those are just labels. So we can, some people say without loss of generality, assume that student 1 is born on day 1. Because he has to be born on some day, and we'll call that day 1. So now we're asking, what are the chances that student 1 has no FOCS-twin? What that means is that all other students are born on days, 2 up to B. So that's B minus 1 days. So B minus 1 outcomes. So, so student 2 has to be born on day, on days 2 to B, which are B minus 1 outcomes, out of the B outcomes that are equally likely for student 2. So the probability for student 2, to be born on days 2 to B is just equal to B minus 1 divided by B. Okay, because, it's a uniform probability space. If student 2's birthday is picked uniformly, then the chances of it being the chances of that outcome being one of these B minus 1 is the number of outcomes that I'm allowing in my event divided by the total number of available outcomes, which is B. And it's the same thing for student 3, and it's the same thing for all students. For example, student 200. They're all, B minus 1 over B, B minus 1 over B. Okay? So all students being born on these B minus 1 days have the same probability, B minus 1 over B. Okay, so the probability that student 2 and student 3 and student 200 are all born on that day is the probability of a big and by independence considerably simplifies this calculation. Okay, by independence, okay, the probability that S2 and S3 and all the way to S200 are born in 2 to B is equal to B minus 1 over B times B minus 1 over B times B minus 1 over B. And that's by independence, because these birthdays are independent. So this is independence. Okay, but this is just B minus 1 over B raised to the power 199. Okay, so let us write that down as the probability that student 1 has no FOCS-twin. Okay, so this is equal to B minus 1 over B. Now, if we wanted to, we could say that, well, 199 is just n minus 1, but, for the moment, I'll just keep it as 199. Okay? And if we plug in the numbers, the number of birthdays is 366, so this is 365 over 366 raised to the power 199. Okay? That's the probability that student 1 has no FOCS-twin. Okay? So the chances that student 1 does have a FOCS-twin, if we compute this is approximately 0.58. So the chances of no FOCS-twin is 0.58. So the chances that I succeed with student 1 are approximately 42%. Wow! So it doesn't look like such a miracle anymore, because the first student, my chances are roughly 4 in 10, almost 50% that I will succeed in finding a FOCS-twin. Okay? So it's not that much of a coincidence when you actually sit down and compute the probability. Okay? Now, let's see what's the probability if I fail. Okay, that's the chance. But if I fail, maybe I'll try the second one. So what's the probability that the first and second fail? So probability that S1 has no FOCS-twin and S2 has no FOCS-twin. So probability of A1 and A2. What is that? Okay, so let's analyze that in the same way. Okay, so now, the first student is born on day 1. Okay, now the second student is born on what day? Okay, if both of these guys have no FOCS-twin, then this student cannot be born on day 1. So there are B minus 1 choices for the second student. So this is the probability that, probability that S2 is born on the days 2 to B, and, S3 is born, S3, S4, all the way up to S200 are not born on the same days. are not born on days of student 1 and student 2. Okay? So that's the case. That's the situation where both student 1 and student 2 have no FOCS twin. Student 2 cannot be a FOCS twin of student 1, and it must be the case that all the other students are not FOCS twins with either student 1 or student 2. Okay? So this is because these birthdays are independent of this guy. This is the probability that student 2 is born on the days 2 to b. So that's b minus 1 over b. We just computed that probability. There are b minus 1 outcomes available for this guy's birthday, okay, out of the sample space of b, times the probability, okay, that S3 to S200 avoid both these birthdays. Okay, but now, student 2 has to be born on Sunday, let's say September 11th. Okay, and so we might as well, label that day day 2. Okay, so student 2 is born on day 2, and that leaves student 2 up to student 200, b minus 2 days on which they can be born. So each of them will be born on those b minus 2 days with a probability b minus 2 over b, because they have b outcomes in the sample space, and the number of outcomes in the event that we are considering is b minus 2. And since there are 198 of these students, we have to multiply 198 of these by independence. Okay, so this is going to be this raised to the power 198, and that's from independence. And that's also because of independence. So we multiply the two probabilities, and to get this probability, we multiply this probability 198 times for each of the 198 students. Okay? And so this result is b minus 1 over b times b minus 2 over b raised to the power 198. Okay? Okay, so let's write that down. So the chances for me to fail are, fail with students, my first two students is b minus 1 over b times b minus 2 over b raised to the power 198. Good. Okay. Let's do one more case, and then we'll jump to the general situation. So the probability that I fail with my first three students, A1 intersection A2 intersection A3. So students 1, 2, and 3 do not have a FOCS twin. Okay, same argument. Student 1 is born on day 1. Student 2 has to be born on one of the b minus 1 remaining days. So the chances of that are b minus 1 over b. Student 3 has to be born on one of the b minus 2 remaining days, which we can call day 3. So student 3, whatever it's born on, we can call day 3. But there are b minus 2 choices for student 3. Okay, so we multiply that. Okay, and now there are 197 more students who have available only b minus 3 days in the event that we are interested in. So the chances of that are b minus 3 over b raised to the power 197. There are 197 such students. Okay? And if we continue this argument, the probability of, the first k students not having a FOCS twin, A1 intersection A2 intersection all the way up to intersection AK. Okay, now you see the pattern. It's going to equal b minus 1 over b times b minus 2 over b times b minus 3 over b, and you have to go all the way up to k, so times b minus k plus 1 over b. Okay, and then the remaining students have to choose among b minus k birthdays. Okay, and how many students are there? 200 minus k. And if we now want to generalize this formula to n students instead of 200, this would just be n. Okay. So you can see that there are two basic parameters, the number of birthdays you have and the number of students you have. And now we're asking, what's the probability that when you pick 1, 2, 3 up to k students, none of them have a FOCS twin? Okay. I will box this. Now in our example, n was equal to 200 and b is equal to 366. Okay, so 366 days and 200 students. So let's go ahead and see what are my probabilities. The probability that I succeed by the second student turns out to be approximately 60 odd percent. Okay, so it's approximately 66%, 66.3%. The probability of my succeeding by the third student is 80%, 80.4%, 88%. 88.6%, 93%, 93.3%. So the chances are more than 90% that by the time I hit the 5th student, I will have found a FOCS-twin. And if I go to the 10th student, it's 99.5%. And if I go to the 25th student, the chances of failing are basically basically minuscule. 99.999%. 99.999% that I have succeeded by the 25th student. And by the 100th student, basically 100% to numerical precision. So, in practice, you'll never have to go beyond 10. Okay. Now, what about if my class had 367 students? Okay. Is it guaranteed that there are FOCS-twins? Yes. But with 200 students, it's not guaranteed that there are FOCS-twins. Okay. So it's possible to completely fail, but the chances of that happening are minuscule, and that's due to the independence and the multiplying of the probability. If there are 367 students, you have to find a FOCS-twin eventually by the pigeonhole principle. Okay, let's do a quick application. Birthday paradox. So a quick application of this, analysis. Okay, now we analyzed it for FOCS-twins when I pick students one by one in the class, but the typical way in which this is presented is a much simpler setting called the birthday paradox. 50 people are at a party, so 50 people at a party. What are the chances of 2 people having the same birthday? We can call them party twins. Okay, so chances of party twins. 2 people having the same birthday. Okay, so basically you can think of it as the same game we played in FOCS, but you ask the first person, do you have a party twin, second, third, fourth, and you keep going up to the 50th. So we can ask, what are the chances that, all 50 people don't have a party twin? So we want the probability that, student 1 and student 2 and all the way up to student n, which is 50, do not have a party twin. Okay, and we can now just use this formula. It's going to equal. Okay, in that specific example, B is still, B is still 366 because we're interested in, birthdays. There are 366 birthdays, and N is now 50. Okay. But K, we're interested in all people not having a twin, so K is equal to N, which is equal to 50. So this is the special case that arises in the birthday paradox. Okay, and so this is equal to 365 over 366 times 364 over 366 times 363 over 366 times ... Okay, so we keep going up to 366 minus 50 plus 1. So 366 minus 50 plus 1 is 317 over 366 times, B minus K, so B minus 50. Excuse me, 366 minus 50 over B, but that's all irrelevant because N equals K, so 50 minus 50 is 0, so this is something to the power of 0, which is 1, so times 1. Okay. And if you compute this number, it's approximately equal to 0.03. So the chances of no party twin is 0.03. If you ask the first person, do you have a twin, second, third, fourth, and make it all the way to the 50th, and none of them have a twin, it's exactly this problem as we just described, and 97% chance that you will find a party twin. So chances of party twin equals 97%. Wow! Okay. And that's why it's called a paradox. Okay. In such a small party of 50, the chances are so high that 2 people will have the same birthday, even though there are 366 birthdays. And that is so surprising a coincidence that it has been called a paradox. But there's no paradox. It's not really a paradox because, when you compute the probability using independence, you get that it is almost for sure that you will find a pair of party twins. Okay, now let's erase, and I'm going to show you the application of this fantastic formula to this very important algorithm in computer science. Let's keep the formula.